All right, so keeping moving along here with properties of gases. It is important to recognize that gases have mass. So often we think, just the air around us. Obviously, there's a significant amount of gases in the air around us: oxygen, nitrogen, carbon dioxide, water vapor, etc., that has a significant mass. And I'm going to go ahead and do some demonstrations with that as I move along. But it is important to recognize that gases do have mass. That allows for the fact that they exert pressure. To be able to exert pressure, you do need that mass as well. Another property of a gas is it's easy to compress. Solids, liquids, because those molecules are so tightly compact, you can't really compress them. A gas, on the other hand, you can compress very, very easily. You can squeeze gases, whether it's a balloon, whether it's a syringe. If you had a syringe and you were able to block the tip of it, you could easily press the gas, basically because there's so much space in between those molecules. Another property of gases is that they diffuse through each other quite easily. That's because they're moving so rapidly. They're not being held on to other molecules in those intermolecular forces like solids and liquids are. So as one molecule of gas escapes from those forces that are holding them together, they can move through other gases quite easily. You know this as if you're home cooking a delicious batch of cookies, you can smell the cookies in the air. If propane is leaked, obviously propane doesn't have a scent to it, but the makers and the producers of propane put the smell in it so that if there's a leak in a propane tank or in a valve or whatnot, you can smell the propane. Obviously, it's diffusing through the air. So that's something that gases do quite easily. The pressures that I was talking about, exerting pressures, but pressures of gases also depend on the temperature. Because the molecules are moving around so fast, again, if we think about an enclosed gas, a gas inside a tire outside and on your vehicle, when it's warm, they're moving. The molecules are moving around quite rapidly. When it cools and it gets very, very cold, like in the wintertime, then the gas particles will start to slow down. They won't bang up against the inside of the tire as much anymore. So it's very common to go outside in the middle of the winter when it's a very, very cold night and you notice that your tire is soft, it's flat. It doesn't mean that you've lost any gas and that you should put some more air in your tires. It just means that it's very, very cold, and as soon as you start driving on the road, that those gases, because of friction, will start to heat up and your tire will expand. I was talking to someone the other day who was laughing about the fact that one of his high school buddies, a friend of his, posted on Facebook how she couldn't believe that she went out one morning, one of the coldest nights of the year, coldest morning of the year, and her tires were all flat. She freaked out. She had to call AAA to get them pumped up. And of course, her friend liked it on Facebook saying, "You wouldn't believe it. It happened to me as well." It wasn't some magical something that was happening to their tires. It was simply the coldest night of the year. The gases weren't banging up against the inside of the tires as much, and so therefore they deflated. Again, just driving along would obviously increase the temperature, increase the pressure of that as well. So moving along real quickly, I want to talk a little bit about that pressure. Okay, we're going to take a look at a few things about pressure in terms of different ways of creating units and whatnot. But let's first understand standard temperature and pressure. And you've seen the STP before. STP stands for standard temperature and pressure, and it's important because gases are so affected by pressures and temperatures, we do need to have this STP. We've used that 22.4 liters per mole for gases at STP. Obviously, if it's not standard temperature or pressure, then there would be more or less volume for there. But standard temperature and pressure is, let's see here if I've got this all set up. Standard temperature and pressure is 1 atmosphere, that's the unit for pressure, and 0 degrees Celsius. All right, so that's standard temperature and pressure. Obviously, again, it's important for using that to be able to say that we have 22.4 liters per 1 mole. Okay. Now, I do want to talk a little bit about the units and other units of pressure. So let me clear that up here real quick. Units for pressure. You've just seen the atmosphere, ATM, the abbreviation of atmospheres. Pascals. Pascals is the SI unit, PA. I put KPA because we're going to commonly use kilopascals. And then also millimeters of mercury. Millimeters of mercury, the unit is mmHg. Millimeters of mercury, it's just often you use that for barometric pressure. We're going to use these three units and their equalities to be able to convert between pressure. We're going to use these three as conversion factors. So for example, 1 atmosphere is equal to 760 millimeters of mercury, which is also equal to 101.325 kilopascals. So standard pressure is all of those three things. Just like 1 foot is equal to 12 inches, 1 atmosphere is 760 millimeters of mercury. And we're going to hopefully be able to use these for converting as well. I'm going to stop right there and we'll go to the next slide next.